So now that we've fitted the once a day wave and twice a day wave and 3 times a day wave, let's step back and look at the amplitudes of those waves. Again, I'll make videos later that say how we get these numbers. There's some really interesting connections there between statistics and calculus and all kinds of fun stuff. But let's record that the amplitude of the once a day wave was about 2000, like we said. The amplitude of the twice a day wave was a fair bit smaller. The amplitude of the 3 times a day wave was even smaller. That vertical shift that we said was about 3000, we can think of that as a 0 times a day wave. How much does it wave? Not at all. So then once I have those, I can plot them against the frequency and say, here at a frequency of 0 times a day, I have an amplitude of 3100. At a frequency of 1 times a day, I have an amplitude of almost 2000, etc. So this plot is called a spectrum of the of what's going on, and let's make it clear that the x-axis here is the frequency of the wave, how many times per day. And the y-axis here is the absolute amplitude. It is sometimes interesting to plot the non-absolute amplitude to see if some waves are flipped upside down, but mostly for spectrums we plot either the absolute amplitude or even the square of the amplitude, which has its own interesting stories. So that's the spectrum, and we can see that as we go higher and higher into the faster and faster waves, the amplitude seems to fall off, and that's not a surprising thing. That happens with a lot of waves. So far we've only done this for one data set. Maybe I just cherry-picked the data set to show you this interesting phenomenon, or maybe it happens in other places too. So let's go look at another data set. So here I have the average temperature in Fahrenheit in Ann Arbor, Michigan for each month of the year. I got it from a data set. I've got the link right there if you're really interested. And I've fitted a sine wave to it, the best possible sine wave. And then let's look at the residuals, which are, let me zoom out. Do you see a wave in there still? Well, I see a twice a year wave. Peak, valley, peak, and then the next valley kind of starts there and ends over there. So you could say that temperature throughout the year, at least in Ann Arbor, is pretty close to a sine wave, but it does have some twice a year fluctuations to it, or some systematic non-sinusoidal behavior. And now you might be saying, well, maybe he cherry-picked Ann Arbor, right? I've got data for another city I'm familiar with here, San Diego. And we can just paste that in, and we see the best fitted sine wave to that. And then when we look at the residuals again we see a twice a year wave. It would be hard to see a 3 times a year wave because we've only got 12 data points here, but we're kind of guessing it would happen. So far we've said I know what the basic frequency is, like 1 cycle per day or 1 cycle per year, but there's lots of situations where we don't know what the main frequency is. And so what do we do then? Well, I've got a tab here called unknown frequency, where I had generated a pure sine wave or cosine wave or something using some frequency, and I've actually forgotten what frequency that was. So what can we do to discover what frequency this is? We could fit a function and try to adjust the frequency of it until we get a good match, and that's not a bad idea. But a more interesting thing we can do, and I know there's a lot going on here, instead of just trying once a day or once a year, we can just try sine waves of a whole bunch of different frequencies and see how well each of them fits. And that's what we're doing here. So we're saying at these different frequencies, what is the amplitude of the best fit wave, which kind of indicates how well it's fitting. And this a wave at this frequency, 6.1 probably, 0.61, seems to fit better than any other of the frequencies we tried. So that would be our best estimate of the overall, of the main frequency of that wave. There's interesting stories behind the little bumps here. That's because as we're trying different frequencies, we only have, what is this, 6 or 7 waves. And so if we try a wave that has a different wavelength, it'll end up kind of overlapping better in some spots than others. And that happens as we cyclically as we change the wave that we're fitting. So that's why we get these bumps. And it's related to something called the sinc function, which is sine x over x. But you can ask me about that some other time. So let's go play with this idea of the spectrum and fitting waves to functions.